Thanks very much. Thanks very much for coming. Can you actually hear me in the back there? Yeah? Good. Okay. So I'm very glad to be here. I almost couldn't make it because of the trains, but have arrived just in time to tell you about the human journey of how we have come to understand the modern cosmological model, and the fact that it requires people from all over the world working together in order to solve the mysteries of the universe. And cosmologists, such as myself, basically wouldn't have a job if it wasn't for one fact, which is that the speed of light is finite. So that means when we look out into the distant universe, we see things as they were a very long time ago. So making measurements of the distant universe allows us to use the universe essentially as a time machine and peel back the layers of time to see how things were in the past. So I'm going to start with the oldest light that we can see in the universe, which is called the cosmic microwave background. And in order to situate ourselves in that context, let's remember that we all live in a galaxy. And when we are looking at the sky, we are looking through a galaxy. So many of the images that I'm going to show you later are looking at the sky and taking the spherical projection and opening it out. And so you see the full sky on this kind of elliptical projection. And along the plane, you see our galaxy. And now as we go to longer and longer wavelengths, you see the sky differently. And when you come to the microwave, and you turn up the contrast by a factor of 100,000, you start to see the cosmic microwave background. So this is the very early universe, about 380,000 years after the initial time, after the Big Bang. And now the universe is 14 billion years old. So this is a baby picture of the universe. And along the axis of the plane of the galaxy, you see this emission from our own galaxy, the red. But above and below, these mottles of green and blue are tiny variations in the density of the universe at this very early time. That is the seed from which all of the structures in the universe that we have today have grown. So let me start out with the discovery story of the cosmic microwave background. It was just a couple of people, Penzias and Wilson in 1964. They were working with an experimental radio telescope at Bell Labs, and they found it by accident. They saw a hiss in their data. It was coming from all over the sky, and they couldn't work out what it was. They even got into the telescope and cleaned out the pigeon droppings in order to try to get rid of this hiss. Recently I learned that the pigeons had a bad fate because, you know, when you take away pigeons from a site, they home. So I understand the pigeons were actually shot. But the hiss didn't go away, and they gave their lives in vain because that was the cosmic microwave background. That was the leftover heat of the Big Bang. And they got a Nobel Prize for their trouble. I'm going to fast forward to the early 90s when the COBE satellite actually measured the temperature of this microwave background. So it's a very cold temperature. It's about 3 degrees above absolute zero. And COBE did something even more fundamental than that. So if you look at this light very carefully with very high sensitivity, you start to see tiny variations from place to place in it. And this constitutes the primordial ripples from which everything else then grew under the influence of gravity. So now it's not just two people. Now the teams are growing. It's funny to see my colleagues wearing these funny costumes from the 90s. I'm not really sure if the younger members of the audience actually recognize that object in the background. That's a computer. So, you know, so now teams of people are starting to come together to study this data and try to work out the origin of all of the structures in our universe. I'm going to fast forward another decade, and this is something very close to my heart because I worked on this experiment as a PhD student. This is the Wilkinson Microwave Anisotropy Probe. Try saying that faster a few times. And so this satellite actually was way beyond the orbit of the moon at the Lagrange point, the L2 Lagrange point, and from that very stable environment measured the temperature fluctuations of the early universe with very high fidelity and made this map. This is a full sky map of the cosmic microwave background. So this is a picture that was taken on the day that we first got our cosmological results from the first 6 months of data from that experiment. I'm very fond of the picture. I can see myself in it as a PhD student, but you can see that the size of the teams are growing. And this is David Wilkinson on the right-hand side. He was one of the pioneers of the cosmic microwave background field, and he passed away as we were analyzing the first data. So the satellite was renamed after him. So what is this cosmic microwave background? So the early universe was very hot. It was so hot that individual atoms were dissociated into their nuclei and their electrons. And light couldn't really get very far because it kept scattering off all of these free electrons, this sea of electrons that permeated the universe. As the universe expanded, it cooled, and eventually neutral atoms formed, and the light was suddenly freed to travel through the mists of time to us, and only really essentially encountering any other matter at the time that they get eaten by our detectors. So they're carrying messages from the early universe, pristine messages, and they've had these incredibly lonely journeys till they reach our detectors. And when we look at this data, what we're seeing is a cosmic tug of war. It's a battle between gravity, which tends to make things compress, and pressure, which tends to push things out. So when you have this sea of electrons and photons in the early universe, and you have gravity compressing and pressure pushing them out, what you do is you set up sound waves in this fluid. And it's these sound waves that, as the universe expanded and cooled and eventually became neutral, that you see frozen in time. And these little fluctuations, these little ripples, tell you about the constituents of the universe and its initial conditions. So you can take these visual sound waves and actually convert them into sound. And you see something like that, where it's not a uniform hiss, right? You can hear a scale in there, a precise frequency that denotes a fundamental scale in the early universe. So we can't actually make universes, right? Which is a good thing. We can't actually fiddle around with the universe and change its parameters and see what it looks like, but we can simulate them in the computer. So this map that we make of the microwave sky is like a fingerprint, and what we do is we make lots and lots of models for the different kinds of universes that there could be and compare them with the actual data that we get. And that allows us to weed out a whole bunch of models that don't work and just keep the ones that do work. And when you do this, you find that actually all of this complex data can be described by just a handful of parameters, which is an amazing thing in itself. That could be completely unexpected. And this cosmological model that we have worked out has ingredients in it, including when did the first stars form, what is the relative fraction of atoms and dark matter in the universe, what is the geometry of the universe, how old is it, and also how clumpy are the initial conditions from which structure formed. So this story was established by WMAP, and we can now kind of follow through what happens. So we're going to zoom into one of these colder than average areas, which is essentially an overdensity in the early universe. So the early part of its history is very boring, dark matter collapsing into clumps. But eventually the first stars form, and their light reionizes the universe because they're pumping out lots of UV light. And then structure forms along filaments and streams. And you can see the universe start to look like it does in the modern day. And when we're observing the cosmic microwave background, you're looking back through all of that turbulent history back to these pristine initial conditions from which we can work out the physics of the universe. Now fast forwarding another decade, this is the Planck satellite, it's a European satellite. It's the first European satellite to study the cosmic microwave background. It made an even better map, higher sensitivity and higher resolution. So each stage is like you put on a new pair of glasses with better prescription and you see better. And when you see better, you can work out more details about what the universe was like. So now the teams have grown tremendously. There were two teams. This is just one of them, and there are still people missing there. So this is a very nice example of European cooperation because all of the countries of Europe and also the US collaborated in this experiment. Lots of different languages, meetings are very interesting, styles of working in different countries are very interesting, and yet all of these people came together to try to work out what is the universe like. Here is an animation of the Planck satellite. So this is a brilliant instrument. It can measure differences in temperature across the sky of a millionth of a degree. And to do that, it had to be cooled to 0.1 degrees above absolute zero. And when it was actually operating, it was basically the coldest place known in nature. It was colder than anything in nature. So with this kind of map, you can see the improvement in the data quality. So here's COBE transitioning into WMAP and then transitioning into Planck. And by looking at this quality of data, we can, for example, work out that the age of the universe is 13.82 plus or minus 0.05 billion years. That's percent precision. So you can work out the age of the universe with that accuracy because the measurements are so good and so precise and so well calibrated. And the data are so good that you can actually try to rewind the clock even further back in time and try to work out something about where did all of these initial fluctuations come from. And in fact, we can try to rewind it back to about 10 to the minus 32 seconds after the initial time. This is a time in which something very strange seems to have happened to the universe. It seems to have expanded by a factor of about 10 to the power 30 in about 10 to the power minus 31 seconds. A big superluminal expansion. And during that time, tiny little quantum fluctuations in a fluid called the inflaton actually got generated and then got stretched out by the superluminal expansion, and that is the origin of structure. So this is the story that we have worked out. It sounds like science fiction. So how can we actually test this idea? So one of the really interesting benefits of this model is that it makes precise predictions. And for example, it makes predictions for the relative level of power in the initial conditions, which is at long wavelengths compared to short wavelengths. So that might sound very counterintuitive, but you can actually think about it in terms of music. So large scales are the bass, and the small scales are treble, and a treble-heavy universe would sound like this. And if you had more power on the large scales compared to the small scales, it would be a bass-heavy universe, which might sound like this. And what inflation does is it predicts that actually the universe is not treble heavy or bass heavy, but roughly balanced, universe that might sound like this. I always have trouble stopping that. So when we actually look into the sky and measure this relative power, we basically find that it's roughly balanced in the way that inflation predicts. It makes other predictions as well. And it's not the only theory that was actually the only game in the market here. So there were many other ways to generate this original structure. And they made different predictions as well. They made precise predictions about the pattern of these hot and cold spots you would see on the sky. And when we actually looked at the data, those theories could be ruled out. So these data also tell you about what physics isn't like, as well as what it could be like. And it also tells you about the dark universe. So by looking at this data, we have worked out that basically everything in this room, everything that is tested at the Large Hadron Collider, all of the baryonic content of the universe is currently a tiny fraction of the energy budget of the universe, about 5%. There's about 27% dark matter, and the rest is dark energy. So for dark matter, we have many theories, which are extensions of the standard model of particle physics, that we can plausibly test in the lab. Whereas dark energy, which is making the expansion of the universe accelerate, is essentially a term for, we don't know what it is. So it is a very unknown piece of physics that is actually one of the biggest conundrums in all of physics right now. So when we look at the late-time universe, we are seeing these island universes, the galaxies. So here, this is not a simulation, actually. This is an animation, a fly-through of the Sloan Digital Sky Survey. And in this volume, there's about 400,000 galaxies. So each of these individual pictures is an actual galaxy out there in the universe. I could look at this for hours. It looks like it's a bunch of fireflies, and like fireflies, these galaxies swarm. They cluster. And they're just the tips of the icebergs of a huge scaffolding underlying the universe, which is dark matter. So I really like this visualization because it shows something like, I think, what the Earth would appear at night. And you would see the lights of the cities, and they tend to cluster where people live. So by looking at the lights of the cities on the Earth at night, you can try to work out what is the population density as a function of the area of the universe. And similarly, galaxies trace dark matter in a biased way. I wasn't here, sadly, for Carlos's talk, but I'm sure you talked about dark matter a lot. So what we can see is the galaxies. There are indirect ways, like weak lensing, to try to get at the dark matter underlying that. And also, it's very important to make simulations which are essentially predictions for what the galaxy formation mechanism lying on top of this dark matter is. And all of these ingredients can be again brought together almost as a detective story to try to understand the physics behind the universe. And this also requires an incredible effort from people all over the world. I'm currently part of the Dark Energy Survey, and we just made a map putting where people came from that work in that survey. You can see it's a global effort. There are some very interesting little islands over here. This is Mauritius. There's somebody from there. I was actually born in Sri Lanka. There isn't actually a point for me there because now I work in the UK. But you can see a global enterprise of people trying to come together to unravel the secrets of the universe. This is the Blanco telescope from which the Dark Energy Survey is made. It's in Chile. And if you look closely, this image is made up of all of these little images. Can you see that? Those are all the women working in the Dark Energy Survey. So there's lots of people that are coming together to work out the secrets of the universe. The survey that I'm most excited about in the coming years is the Large Synoptic Survey Telescope. So here, this is an enormous effort. It's 10 years over which we are going to make a movie of half the sky. We're going to repeatedly visit every part of the sky on a fast cadence and observe the universe as it fluctuates in time. We will see explosions coming from supernovae. We will see objects in the solar system. We will see galaxies, stars moving. And all of these things are going to lead to 30 trillion measurements in that time. So this is really big data astronomy. And in order to understand and process this data, this is essentially, it's a great, amazing telescope, but it's also a software project. It's basically trying to make sense of enormous volumes of data and pick out science out of that. So this survey has many different science collaborations, and I'm part of the dark energy science collaboration. So we took a picture of a whole bunch of us who got together at SLAC at Stanford last week. And here's a whole bunch of people, again, from all over the world. This collaboration is quite interesting because it's not just astronomers or cosmologists. It's particle physicists as well, and computer engineers, and people that actually do statistics and informatics. So they are all coming together from all these different disciplines to try to make sense of this data and learn the secrets of the universe. And as we go on into the next decade, so I've showed you cosmic microwave background data, I've showed you galaxy surveys, but we are going to measure the universe in a whole range of wavelengths, ranging from gamma rays, very high energy photons, all the way to the radio, from experiments like the square kilometer array. And so I put all of the E and M part of the spectrum on one side, because now we have started to measure the universe also in gravitational waves, very high frequency gravitational waves, and there are options for seeing gravitational waves at larger wavelengths as well with future experiments. I'm sure you had a fantastic talk about that earlier. So we are going to be seeing the universe in very different ways and trying to understand it. And we will need a lot of people coming together to do that, because the cosmological model we've worked out is quite strange. And it's quite strange, including the fact that perhaps it predicts that there are other universes and things like that. Very strange concepts which seem counterintuitive. So I think Martin is going to tell us about the multiverse later. So you will hear from him what this implies. But these are the kinds of riddles that we're faced with in trying to work out answers to what the universe is like. It has thrown up all these new and mind-boggling questions. I'm going to end early. And so I hope that I've convinced you that not only is the process of understanding the universe well underway, but that it actually requires people from all over the world, of all different types and disciplines coming together and combining their expertise in order to work out the mystery. Thanks very much.
So we do have time for questions. Please raise your arm and wave it. It's a bit dark in here. Everyone totally convinced?
Is it too late in the day? Oh, yes. Hello.
What inspired you to become an astrophysicist?
Okay, that's a very hard question. Carl Sagan, reading science fiction, good teachers at school, many answers to that one. But I knew I wanted to be an astrophysicist when I was 5.
Actually, I've got a sociological question as well.
Okay.
This business of the size of the teams, do you think it's going to reach a sort of critical point where it's just too big? I don't mean necessarily your collaboration, but in general. I mean, we know particle physicists have masses of people, and astronomers are heading in that direction.
That's an extremely good question. So in the teams I'm currently working on, there are up to 500 people, right? And I don't think that the particle physics style of working is going to work for us. That's because the problems that we are trying to understand are much more diverse. And also astronomers come from a much more individualistic style of working than particle physicists. Writing the publication policy for the dark energy science collaboration at SST has been interesting because everybody from the particle physics side is used to working in a certain way, and astronomers are completely a different way. And I do believe that there is an interface at which those sets of people can meet. And what's going to happen is that there will be very large collaborations, but there'll be individual teams within them working on different parts of the problem. And then the whole collaboration will put those things together. So you still get the pleasure of working with a small team of people that you really love working with, while benefiting from this very large-scale infrastructure that we can build. And I think that can happen to a much larger level than 500.
Indeed.
Yeah.
I must say I prefer my teams who can fit in a taxi like
Yeah.
Any more? Or?
Yes.
Yes.
Yeah.
Simple question, Gary. Do you think, so humanity decided to spend all this money, billions, you think the basic problems like the nature of the dark energy will be resolved in the next generation of experiments like LSST?
Okay, so you asked about dark energy. If you had said dark matter, I think it is an experimental question, but dark energy I really think is a theory question. We need to understand general relativity better, and we need to understand quantum gravity better to really solve that problem. But what experiments can actually do is to put constraints on how those theories can diverge from reality. So I think it's actually something that's much more of a theoretical problem than an experimentally accessible problem. Unless we start to make universes in the lab, in which case we should all be scared.
So when you gave this very precise measurement of the age of the universe,
Yeah.
so there's an uncertainty in there, which is the uncertainty in the measurement.
Mm.
I'm not sure, this may not be a question that means anything, but anyway, when you said that a big fraction of the universe is dark energy, we don't really have any clue what that is.
Mm.
So could that change completely, this number, or do we have some reason to be confident that measurement is a solid measurement?
Yes, so that's an extremely good question. So that measurement, the uncertainty that's in there, is based on measurement uncertainty, but there's a model uncertainty on top of it, which is what you're alluding to. So when you change the cosmological model and you make assumptions that are different from assuming that it's spatially flat, for example, and there aren't extra components in it, then those numbers can change a bit. Currently, just with Planck alone, the number might change a lot, but the moment you add one extra data set, it still, again, becomes quite constrained. So I don't think the age of the universe is going to fluctuate very much. But there are other parameters about the cosmological model that could have bigger error bars based on what assumptions you make about the ingredients that you put into the simulations of the universe. Does that answer your question?
Okay, you're not going to suddenly find that it's wrong by a factor of 2.
No, I don't think that's going to happen.
Okay, I think we should thank Hiranya again.